Hi, we present stable object placing using curl and diff features of vision-based tactile sensors. When an object makes initial contact to a surface and some force is exerted, the moment of rotation caused by the instability of the object's placing can cause the object to rotate in a certain direction. The direction of corrective rotation is clockwise when the force application point is on the right side of the vertical line, and counterclockwise when the force application point is on the left. If the force application point is on the vertical line, the object does not rotate. The sign of the torque at the force application point indicates the direction of corrective rotation. The torque is positive, indicating clockwise rotation if the force application point is to the right side of the vertical line, negative for counterclockwise rotation if on the left. If the torque is zero, the force application point is on the line, indicating that the object does not rotate. We make assumptions for our model. As shown in the figure, the force application point is in the area where the object can be placed stably. Under this assumption, manipulating the object so that the detected torque is zero results in a stable placing. To realize stable placing, the robot arm is controlled by admittance control. The end effector velocity of the robot arm is calculated by equation 1 to achieve the target wrench. The direction of corrective rotation of the object can be estimated based on the sign of the torque. While the method using the force-torque sensor can estimate the direction of corrective rotation, it is prone to inaccuracies primarily due to the cable tension and sensor noise. This study uses gel-site tactile sensors instead of force-torque sensor. Our method estimates the direction of corrective rotation of objects using the displacement of the black dot pattern on the elastomeric surface of gel-site. We calculate the curl from vector analysis, indicative of the rotational field magnitude and direction of the displacement of the black dots pattern. When the object is pressed against the desk, a torque is generated that attempts to rotate the object. This torque is transmitted to the gel site and results in a shift in the position of the black dots on the gel site, which represents the applied torque. This torque at the contact point on gel site can be observed as the displacement of the black dots on gel site. From the red arrows in figures, when the left side of the object contacts the desk, we observe a displacement of the arrows representing the black dots on the gel site moving in a specific rotational direction. If the right side of the object is in contact instead, the arrows exhibit the opposite rotational movement. Simultaneously, we calculate the diff of displacement between the left and right fingers' gel site's black dots. When the object is pressed against the desk, a torque is generated that attempts to rotate the object. This torque is transmitted to the gel site and is exerted as shear forces in opposite directions on the right and left gel site. This makes a difference in the displacement of the black dots in gel sites between the left and right fingers. On the side where the object is in contact, the displacement of the black dot is represented as an arrow pointing vertically upward. This displacement is noticeably larger compared to the side where the object is not making contact. Our robotic system features a 7 Franca Amica Panda arm. This robotic arm is equipped with a custom-designed parallel gripper. The gripper features vision-based tactile sensors, known as gel-site mini. A Leptrino force-torque sensor is mounted between the robot arm and the gripper. We conduct experiments where a robot grasps objects and places them on a desk to evaluate our proposed system. To aid evaluation, an RUCO marker is placed on the object, and the object's pose is measured when the object is placed on the desk. The displacement is then calculated by comparing the object's pose initially in its manually stable state on the table with the final pose achieved through the robot's stable placing process. For the evaluation, we chose 18 objects considering various factors. The force-torque-based method often failed. There were many failures that resulted in the object toppling over in the force-torque sensor-based approach. There were also failures that the object's tilt was kept after contact between the object and the desk. Moreover, some were seen where the robot arm applied force in the direction that the object was to be upright, but the object passed through the upright state and toppled over. The tactile-based method achieved high accuracy for a variety of objects. Additionally, the method was also robust against cracks in the sensor of the surface and manufacturing differences in the size and shape of the black dots. The proposed tactile sensor-based approach can achieve stable placing with high accuracy less than 1 degree error, in nearly 100% of cases across all objects, highlighting its potential as an effective fork sensor alternative. Even if the robot is disturbed during the stable placing process, it can be seen that stable placing is still achieved. In summary, we propose a method for stable object placing using tactile sensors. By estimating these two object directions of corrective rotation from curl and diff, the robot can manipulate the object's pose for stable placing. This method of estimating the direction of corrective rotation is robust against sensor failures, such as cracks in the surface and manufacturing differences in the size and shape of the black dots. In experiments with 18 objects with different characteristics, the force-torque sensor-based method fails because it misrecognizes the direction of rotation for objects other than those with a large support polygon due to sensor noise and cable tension. In contrast, the proposed tactile sensor-based approach can achieve stable placing with high accuracy in nearly 100% of cases across all objects.